All right, so please make sure that you are comfortable with calculating moles per liter before you really try to get into this video. If you don't quite get how moles per liter works, this video is going to be a little bit hard to digest. So, if you recall, ionic compounds dissociate. Remember, that means that they break down into their component ions. So, simplest example ever, if we have NaCl, we toss it into some water, we are going to get Na plus aqueous ions, and we will also get Cl minus aqueous ions. Ionic concentration means the actual moles per liter of each type of ion in a solution. So if you notice in this dissociation equation, remember we're adding a solute, we're adding NaCl solid to water, and we are forming aqueous ions. What ionic concentration would tell us if I dissolved, for example, 1 mole of sodium chloride in however much water we're talking about, I would get 1 mole of Na plus aqueous, and I would also get 1 mole of Cl minus aqueous. By the same exact logic, let's use a decimal. What happens if I dissolve 0.5 moles of sodium chloride in an amount of water? Okay, well, that means that I would get 0.5 moles of sodium ions, Na pluses, aqueous, and I would get 0.5 moles of Cl minus aqueous. You can see where we're going with this. Since there is that, remember, there's always an implicit or automatic 1 in front of things that we don't have any numbers in front of. It's like an automatic coefficient of 1. That means that whatever number we have here is going to be the same as the numbers there. Okay. What happens if we have a different ionic compound? What if I have a different ionic compound like, I don't know, calcium chloride? So CaCl2 solid. If I dissolve this chemical in water, we're going to have a Ca ion, because there's only one Ca ion in this formula, and a Ca calcium ion has a charge of +2. How many Cl minuses are we going to have, though? We're going to have 2. So we have 2 Cl minus aqueous. Interesting. In other words, if I dissolved 1 mole of calcium chloride, and remember, I don't care about the mass right now, we just care about moles. We're always starting the basic way. If I have 1 mole of calcium chloride, remember there's a 1 in front, that means I'm going to have 1 mole of Ca2 plus ions, but we're going to have 2 moles of Cl minus ions. Why? Because there's a 2 in front of the Cl. Where did that come from? It came from the chemical formula. So we can do that with any numbers. If I say 0.1 mole of calcium chloride. We will have 0.1 mole of calcium ion, and we'll have 0.2 mole, twice as much, of the chloride ion. So one last one, just kind of for the sake of argument, or just to kind of fill it out a little bit. Let's find an ion that will give us a complicated set. Let's do... I'm just looking at different ions, figuring out one that would be kind of interesting. Ooh, okay. Let's use phosphate. And let me just make sure that I'm going to be 100% correct, and I'm going to be dissolving it correctly. No, actually, you know what? Let's use sulfate. So let's do aluminum sulfate. So remember, when you go from the word equation to an actual chemical equation, we need to know the charge of the ions. And I know I'm going way back to Science 10, but this is just a little bit of review so we can get our ionic concentrations understood. So I know that the aluminum ion has a charge of 3 plus, and I know by heart, some of you probably do too, that the sulfate ion, has a charge of 2 minus. That means that I'm going to need the charge of all my aluminums to be equal to plus 6, and the charge of all my sulfates to be minus 6. Remember, the charges in an ionic compound must balance, and because of that, I'm bringing in plus 3's from the aluminum, so 2 times 3 is 6. And I'm bringing in minus 2's from the sulfate ion. I need 3 of those. So the chemical formula of the chemical aluminum sulfate is Al2SO4 bracket 3. So now that was just to figure out what the actual chemical formula is. Now we're going to do the dissociation equation for aluminum sulfate. So now I'm going to dissolve it. This was just to find out the chemical formula. Now I'm going to dissociate this. So I'm going to say Al2 bracket SO4 bracket 3, and we'll say it's a solid. We are going to dissolve that in some good old H2O. We have 2 aluminums, so I will say 2Al3 plus aqueous. And we have 3 sulfates. So 3 out front. Where did we get it from? The subscript, because that, remember, tells us how many of the bracketed polyatomic ion we have. So 3 of those, 3 SO4, 2 minus aqueous. Bam. So if I take 1 mole of this chemical aluminum sulfate and I dissolve it in some water, and again, I haven't talked about concentration. If you noticed, we have not mentioned liters yet, but we will. If I dissolve 1 mole of aluminum sulfate in some water, I'm going to get 2 moles of aluminum ions, and I will get 3 moles of sulfate ions. And again, this is proportional. It's like if you say, okay, 1 bicycle has 2 wheels. How many total wheels do 5 bicycles have? 5 times 2. Boom. So if I have, for example, 0.5 moles of aluminum sulfate. 0.5 times 2 would be 1 mole. And 0.5 times 3 would be 1.5 moles of sulfate ion. So that should make a little bit of sense. We are breaking up these ions and we're putting whatever subscript they had, that's going in front. So Al2, 2 aluminums in this molecule, when it dissociates, when it breaks down into its component ions in water, we put a 2 out front there. 3 sulfate ions in the molecule, when they break down, it's going to give me 3 sulfate ions in the solution. They're all separate now. That's what the numbers in front mean, separate copies. So you don't want to put the 3 down here, and you don't want to put the 2 down here. You put it in front. That tells you how many separate aluminums and how many separate sulfates you have. So let's do a very simple example. Now we're going to bring concentrations into the mix. I'm still going to stick with moles. The next one, we're going to do grams at the start. But for now, we'll stick with moles. So let's say I have 2.64 moles of barium nitrate dissolved in 7.33 liters of water. So the first thing I need to do is my good old dissociation equation. And in order to do that, I need to solve what the chemical formula of barium nitrate is. And since I have all that memorized, I don't have all the periodic table memorized, but I got a lot of it, or at least the most common ones. I know that a barium ion has a +2 charge, and I know that a nitrate ion has a -1 charge. So I'm going to need 2 of those to make my chemical Ba bracket NO3 close bracket 2. So the first step is we figure out what our ionic compound's formula is, and we did that. Now we have to dissociate it, and if you look carefully, when I make my little ionic compound, it's like almost the reverse of dissociating. So now I'm going to do my dissociation equation. So we have Ba bracket NO3 close bracket 2, and that's a solid. We are mixing it with good old H2O. We are going to get a Ba2 plus aqueous, and we are going to get 2 NO3 nitrate ions, and they're also aqueous. Now, instead of counting moles, we're going to count moles per liter. So I need to find the concentration of my original chemical. So my concentration is just the moles number. And I'm still writing units divided by the liters number. And so I'll calculate that on my little TI-84 here. So 2.64 divided by 7.33, and we get 0.36 moles per liter. That means, and I'm just going to go to, let's get that gross green. Yeah, okay, we'll use that. So if my original concentration of barium nitrate was 0.36 moles per liter, remember there's a pretend or implicit automatic 1 in front of here. If there's an automatic 1 in front of here, there's an automatic 1 in front of here, which means that my barium Ba2 plus aqueous ion concentration is also 0.36 moles per liter. When this breaks down, though, it releases 2 nitrates. So I'm sure some of you kind of already in your brain, you're like, I know exactly what he's going to do next. Remember we multiplied this by whatever number was in front for these two? Yeah, same idea. So we're going to multiply 0.36 times 2. So how much, what's the concentration of nitrate ion we have? 0.72 moles per liter. So the key to doing these is you find out the concentration of your original ion, or sorry, your original compound, you dissociate, and then you multiply the original concentration by whatever number coefficient is in front of your dissociated equation. Super, super simple. I'm going to pause and I'm going to do another example on a separate clean page. And here we are. So you might notice a little bit of a difference with this question. We are now in grams territory. We're in Grahamstown. So that means we're going to need to convert moles, or sorry, grams to moles. And that's fine. So the first thing I need to do is find out what is the chemical formula of tin 4 chloride. Okay, well, the 4 there tells me the charge of the tin. That means that inside of this ionic compound, the tin has a +4 charge. Chloride is always going to have a -1 charge. That means I need 4 -1s to cancel out the +4. Remember, we always have to make sure that in an ionic compound, the charges are equal to 0. They cancel out. That means that the chemical formula of this ionic compound is SnCl4. So great, now we know the chemical formula of tin 4 chloride. I can write the dissociation equation, then we'll do the concentration calculation, then we'll do the ionic concentration. So let's dissociate this bad boy. So SnCl4, and that's a solid at the start. Arrow, we're adding it to good old H2O. We are going to, from that reaction, from that dissociation, get an SN4 plus aqueous, and we're going to get a number of Cl minuses. Take a second, look at the above equation, and you'll notice we needed to use 4 to make it. There's a 4 in the formula. That means we're going to have 4 Cl minus aqueuses. Great, there's our dissociation equation. We're rocking this. It's not too hard. So what about the molar mass? Okay, so we have 1 tin, Sn, where is tin on the periodic table? It's always one that I have like struggles finding. Cobalt, nickel, zinc, gallium, tin. There we go. Element number 50. So we have one tin, and that has a mass of 118.71 grams per mole. And we have 4 chlorides. And those guys I remember for sure are 3545. So 35.45 grams per mole. So I'm going to do the little math on my calculator. 4 times 35.45 plus 118.71. And I get 260.51. So 260.51, and that is measured in grams per mole. So now I can go from grams of tin chloride to moles of tin chloride. So over here I'm going to say moles of SnCl4. When we do a mass to moles calculation, we start with the mass. So 11.9 grams. I open up a conversion bracket. We're familiar with those. And I know that my answer has to be in moles, because I'm going to need moles in order to make moles per liter. So conversion bracket here, moles on top, so mole on top, and 260.51 on the bottom. 51 grams. So we are allowed to get rid of the unit called grams. 11.9 divided by 260.51 gives me a tiny number, and that's totally fine. So I'm going to write down the number as text. And remember, I'm going to leave that number in my calculator. So it's 0.0456796 moles. So, recapping so far, we got our chemical formula, we did the dissociation equation, we found out the molar mass of the chemical that we're dealing with, we used the mass and the molar mass to determine the number of moles. Oops, didn't mean to cross that out. Now we're going to do moles per liter. So my moles number is 0.0456796 moles. And I need to divide by the liters of water. This is something that students mess up when they're in a hurry. They might just hurriedly write down, 267. That's milliliters though. The number of liters there is 0.267 liters, dividing by 1,000. So I'm going to calculate that on my calculator, divided by 0.267, and I get another long number. Again, I'm going to write it down here, or write down most of it. 171,085. Again, I'm rounding it just so I don't have a giant string of numbers there, okay? And this is a calculation, and the unit is in moles per liter. And you know, it looks like we have 3 sig digs, and since all of our numbers are going to be in moles per liter, I can just say my concentration of tin 4 chloride is 0.171 moles per liter. So now we go back to our dissociation equation. I know the concentration here, 0.1. Oops. If only I wrote it down properly. 171 moles per liter. My tin ion, SN4 plus aqueous, has the same concentration. Why? Because there's a 1 in front of here and there's a 1 in front of here. So that means that this has the same exact concentration as the concentration of the compound. And then what's the ionic concentration of Cl minus? Well, since there's a 4 there, all we need to do is multiply this concentration of the original by 4. That's like literally it. So 0.171 times 4 is 0.684 moles per liter. So there you have it. We talked about writing a dissociation equation. We talked about moles, how the mole ratio, the coefficients determine the number of moles. And then we extended that idea to the coefficient also determines the concentration, the moles per liter. So again, 1, our molar mass, 2, moles of chemical, 3, the concentration, and 4, we apply the concentration. We multiply by the numbers that are in front. And there you have it.